Hello, grade 11s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabudiwa Sos, Ukobela Maths. And without any further ado, let's look at this question that we have here. Okay, so we have question 7 on limiting reagents. So it says 0.8 gram of ozone O3 is reacted with 0.75 gram of nitrogen 2 oxide NO according to the following reaction. And then we have 7.1, which is asking us to define the term limiting reagent. So what is limiting reagent? The way we define it is we say this is a substance that is completely used up in a chemical reaction, right? And then let's now proceed. We have 7.2. It says now identify the limiting reagent in this reaction by means of a suitable calculations. So here they were supposed to say by means of a suitable calculation. Now, how do we determine that? So you need to follow these steps here. So step number 1 would be to calculate the available number of moles. The available number of moles of each reactant, right? So when we are talking about the reactant, we know that we are talking about these two substances that are appearing before the arrow. So all the substances before the arrow are known as the reactants, and all the substances after the arrow are known as the products, right? So now in order to determine the limiting reagent, because reagent is the same as the reactant, so we need to compare the number of moles of both these reactants. So we want to start with ozone. Let's say calculate the number of moles of ozone. This will be mass over the molar mass. And then we are given that the mass of ozone is 0.8. And then if we have to divide that by the molar mass of O3, we have the oxygen, the molar mass of oxygen according to our periodic table is 16, but then we have 3 atoms of oxygen, so that is supposed to be 16 multiplied by 3, which will give us 48. Then we have 0.8 divided by 48, which will then give us, so if we round off to 2 decimal places, that's 0.016, so that's 0.2. So let's leave it at 2 decimal places. So we have that, and then now we can as well calculate the number of moles of the nitrogen oxide. So that's mass over the molar mass, and then the mass of the nitrogen oxide we are given to be 0.75, and then the molar mass we are going to say nitrogen is 14, and then plus 16. So that is supposed to give us 30. And then now we have 0.75 divided by 30. So that gives us 0.025. So if we round off to 2 decimal places, that's 0.3. And then mole, right? So we have 0.02 mole for the ozone, and then 0.03 mole for the nitrogen oxide. But then now when we compare the ratios, so step number 2 is to compare the ratios to find the required number of moles. The required number of moles of each substance or of each reactant. Now, if we say the ratio of O3 to the ratio of the nitrogen monoxide, we can see from here, remember the ratio is taken from the coefficient. So the coefficient here is 1 because we don't see any number here. And then the coefficient also for that one is 1, right? So that means for every 1 mole of the ozone that reacts, we also need 1 mole of the nitrogen oxide. right? So in this case, looking at ozone, we can see that ozone has the smallest number of moles as compared to the nitrogen monoxide. So that means the number of moles of the nitrogen monoxide that needs to react. So the number of nitrogen monoxide reacted would only be 0.02, because the ratio is suggesting that if ozone has 0.02 mole required, then also nitrogen monoxide needs to react 0.02. But then the available number of moles of nitrogen monoxide is 0.03, which means comparing this number here, the one that is required versus the one that is available, we can see that the one that is required is smaller than the one that is available, making our nitrogen monoxide the excess reagent, meaning we'll still have some of the number of moles in excess. To be more specific, we'll have a 0.01 mole of nitrogen monoxide in excess, because from 0.03 minus 0.02, then we'll be left with 0.01 in excess. But then what will happen to O3? O3 will be completely used up. So the ozone will be completely used up, which makes it the limiting reagent. Remember, when we define limiting reagent, we said this is a substance that will be completely used up in the chemical reaction. So that means, in conclusion, we'll then say, therefore, our ozone, O3, is the limiting reagent. Why? Because the ratio is 1:1, and as we can see here, ozone has the smallest number of moles. So O3 is the limiting reagent. Right. So just like that, you have your 4 marks. So make sure you follow those 2 steps. Number 1, you calculate the available number of moles of each reactant. And then number 2, you compare the ratio to find the required number of moles. Okay, so now we are on 7.3. 7.3 says calculate the expected number of moles of oxygen gas that will be produced in this reaction. Now, if we want to find out the maximum number of the products that can be produced, we are better off having to calculate that using the limiting reagent. So the limiting reagent, this is what you need to note about the limiting reagent. The limiting reagent tells us 2 things. It can tell us how much of the other reactant is needed. Right. So as we saw with the case, we were able to determine the number of moles of nitrogen monoxide that need to react, right, from observing the number on our limiting reagent. So that's one thing that we can find from the limiting reagent. It tells us how much of the other reactant is needed. So if I have to employ an example here, suppose that you are running a sandwich business. So how do you spell sandwich? I don't know how, but then yeah. Then suppose that you are making sandwiches, and then you have 10 slices of bread, and then you also have 4 slices of cheese, right? Now, this sandwich that you are making must be made of what? The ratio of the making of the sandwich is that you need 2 slices of bread to 1 slice of cheese. Now, obviously, if you are looking at this 2 ingredients, you can tell that the number of slices of cheese will be the limiting reagent, since the number of slices of the cheese will be the one to be completely used up, or will be the one to be first used up, right? And then now looking at this case, we have 4 slices of cheese, meaning how many number of slices of bread do we need in order to react all these 4 slices of cheese, or in order to use up all these 4 slices of cheese? From this ratio here, we can tell that if the ratio is 2:1, then that means if we use 4 slices of cheese, then we would have used 8 slices of bread. Right. So what did the limiting reagent tell us? The limiting reagent told us what amount of the other reactant do we need to actually put into the reaction. And then number 2, the limiting reagent can tell you the maximum number of products that can be formed. Maximum number of products formed. So this is also known as the theoretical yield. right? So if we want to determine the maximum number that can be formed, the maximum number of products that can be formed, we are saying we are determining the theoretical yield. In this case, it would be having to ask ourselves, what's the maximum number of sandwiches that we can make from these ingredients that we have here? Now, obviously, looking at the fact that this is our limiting reagent, and then we know that one sandwich will be made out of 2 slices of bread and 1 slice of cheese, then we are able to determine from this that we can only make a maximum of 4 sandwiches, right? Using this these ingredients here. Now, if we were to look at the maximum at the excess reagent, we wouldn't be able to come up with the correct answer to that one, because looking at the number of slices, we might be tempted to say we will be able to produce 5 sandwiches. But then remember, we won't be able to produce 5 sandwiches because here we only have 4 slices of cheese, right? So the last sandwich won't have any cheese. And then that doesn't qualify to be a sandwich if it doesn't have the cheese, because we are selling cheese sandwiches. Right. So that means the maximum number of sandwiches that can be produced is 4. So this tells us what the limiting reagent is all about. Number 1, the limiting reagent will tell us how much of the other reactant is needed. And number 2, it will tell us the maximum number of products that can be formed, which is also known as the theoretical yield. So, okay, now going back to the question, how are we then supposed to apply it here on 7.3? Now, note that we identify this one as the limiting reagent, meaning if we want the maximum number or the expected number of moles of the oxygen gas, we must compare the ratio of the ozone, which is the limiting reagent, to the ratio of the O2. Now we find that we have ozone to oxygen gas, the ratio is 1:1. But then remember the available number of moles for oxygen gas, for ozone meant to say we calculated it to be 0.02. Now, if the ratio is the same, that means the number of moles that air will be produced for the oxygen gas will also be the same as the one that reacted of the ozone. So we also have 0.02. Therefore, in conclusion, the number of moles of O2 is 0.02 mole. Right? So same ratio, same number of moles. Okay, then that's it, 2 marks. So it will be a mark for having to identify that the ratio is 1:1, and then it would be a mark for having to conclude that since they have the same ratio, they must also have the same number of moles. Right. Then 7.4 now is saying, hence calculate the maximum number of moles of gas in the container when the reaction is complete. So now understand this. So we have O3 here, and then we have nitrogen oxide, and then we have O2, and then we have NO2. Now I want you to note this. So this is what we had initially, and then right here, this is what we will have finally when the reaction is complete, right? So initially we calculated the available number of moles, and then we found that the initial number of moles for the O3 was what? Was 0.02. And then also here, because this one we calculated the available was 0.03, right? And then the O2 here, this was 0 initially because we had no products. Remember, initially we had no products, right? So finally, we find out that this one reacted. All of the O3 was used up because this was the limiting reagent. Now, if all of the O3 is used up, that means we were left with 0 here. But then here, according to the ratio of 1:1, 0.02 reacted, and then we were left with 0.01. Right, because 0.02 reacted, but then this one was the excess reagent, right? So this was the limiting reagent, and then this was the excess reagent. Now, remember from the O2, according to the ratio 1:1, what are the number of moles that were produced? 0.02. And then even here, the ratio is 1:1. What was the number of moles that was produced? 0.02. Now, if we want to calculate the maximum number of moles of gas in the container when the reaction is complete, that means we'd have to add everything here on the final, the number of moles final. So that's 0 plus 0.01 plus 0.02 plus 0.02. So the number of moles maximum will now be 0.05 mole, right? And then just like that, you have your answer. So you only show this. And then you conclude that therefore the number of moles maximum is 0.05 mole. So note how we were actually able to do that. Now, to calculate the percentage yield, says calculate the percentage yield if only 0.48 gram of oxygen gas was actually produced on completion of the reaction, right? So percentage yield goes as percentage yield is equals to actual yield over the theoretical yield. So actual yield over theoretical yield multiplied by 100. Now the theoretical yield, I've already explained what is that. It's the maximum number of product that can be produced of that particular substance. So now we are focused on the oxygen gas. They're telling us that the oxygen that was produced is 0.48 actual. But then theoretically, if we had to calculate without any disturbances or any factors that might affect the production of oxygen, theoretically, what will be the maximum number of oxygens that we expect to be produced? Remember, in 7.4, in 7.3, we calculated the expected number of moles of oxygen, right? And then we found that the number of moles of oxygen gas was 0.02. Now we can use that to actually calculate the maximum mass of oxygen that can be produced, which is the theoretical yield. So that's N is equals to M over big M, right? Then if we rearrange this, that's M is equals to the number of moles multiplied by the molar mass, which is 0.02 multiplied by O2 is 16 multiplied by 2, that's 32. And then if we say 0.02 times 32, we end up with 0.64 gram, right? Now, let's read. Calculate the percentage yield if 0.48 gram of oxygen was actually produced. So that means the 0.48 gram goes to what? That's the actual yield, right? So that was what was actually produced. But then the expected number was 0.64. Right. The expected mass was 0.64 multiplied by what? 100. So now we want to find the percentage of the actual versus the theoretical. So what was actually produced versus the one that we expected? So 0.48 divided by 0.64 multiplied by 100. So we get that the percentage yield is 75%. So that's how you were supposed to go about answering that question for a total of 4 marks. So all in all, the question was about 15 marks. So pay attention to everything that I did here.